Hi guys, welcome back to the channel. In today's lecture, we are going to solve one problem on influence line diagram, which we will be solving by using direct methods. Okay, so we'll come directly to the problem over here. In this problem, we are giving one simply supported beam in which is overhang. Okay, this BD portion is basically overhang portion. So we need to calculate the ILT influence line diagram for shear and moment at point C. Okay, the point is given at this section. We need to find how the shear force is varying. Shear force is varying when the unit load is moving along this beam. Okay, so basically influence line diagram we will draw for the moving loads. So here our moving load is nothing but a unit load, right? So in this problem, first we will see when let us suppose we will divide. Okay, so again I will draw this beam over here. This is the D portion and this is point C. This is 4 meter. This is the beam. Yeah. Okay. So first, in the case to draw the ILT for the shear force, what I am doing over here is I need to calculate what is the shear force at a section C. Okay. So basically, in the first case, what I am doing, I am keeping the unit load at this cross section at the left side of the cross section where we need to find the shear force. Okay, so I am keeping the unit load at this location. Let us suppose this is at a distance of x. Okay, I am drawing. What I am solving here is that I am calculating the function for shear force in terms of the positioning of the load. Okay, how shear force is varying with respect to the position of this unit load, that we need to find. Okay, so for first case, what I am doing over here is I am keeping the load at this location, at this between the AC. Okay, left side of the section I am keeping the load. Okay, when I am keeping the load over the left section, let us calculate how much reactions are generated at A and B. Okay, so basic equilibrium equation is RA plus RB is nothing but unit load, right? And if we take moment about this point, RA point, it will give me moment about RA, moment about A point will give RB into 8. Moment due to RB is anti-clockwise and due to this unit load is clockwise moment into 1 into X. Okay. So from here I can write RB equals to X over 8. Right. So if you see if I cut this beam from this section, let us suppose I cut this beam at this section. So it will look like this. This is AC and this is B point and this is our B point. Okay. So at B we find that reaction is X by 8. Okay. Now if I consider this portion, this is, let's suppose this is right and this is left side. Okay, if I consider this portion, so to balance this vertical force, I need to have some vertical force in this downward direction. It will be acting in this downward direction, right? To balance this x by 8 force. So this force will be nothing but it will be x by 8 by summation F by summation of force in along the y direction. Okay. Now at this section, at this C section, to balance this force, there must be a force applied at this location, at this point, in this upward direction. So that must be equal to x by 8. Okay. Now you can see that basic assumption of and our unit load is acting at this point. Okay, and again some RA reaction is generating at this point, right? So for our assumptions for the positive, this is for the positive shear force. For the positive shear force, as we know that this is our positive shear force. In this case, is our positive shear force, right? But you can see over here. Here the case is different, little bit different. It is look like this. This is downward, and this is upward. So this is basically a negative shear force. Okay. So this force is basically this force is basically nothing but this VC is nothing but this is negative shear force. Okay. As we move from this section, so when we move from this section from this side, this type of shear force will be considered as a negative and downward force shear force considered as a positive. So as per our sign convention, this shear force at this section when the unit load is between A and C is negative. So when unit load, so VC is nothing but the function will be VC is x by 8. Okay. So VC will be x by 8. So when x equals to 0, what will x equals to 0, then VC will be equals to 0. Why? Because this total load, one unit load will be taken care by a support reaction from one only. Okay, so this shear force at VC will be 0. So so at this point our shear force at VC is 0. When unit load at this position, shear force at VC will be 0, and this is coming from this expression. Also, you can say that when this load is applied at this position, at this location, it will be taken care of by RA. And in this case, RA equals to unit load. Okay, so these both forces will cancel out each other, and the shear force at this section will be 0. Right? So this is the case. Now, as you can see that the variation is linear. Okay, and its slope is negative. This is y equal to minus of mx plus c. Okay, so this graph, this function should come below this axis. Okay, and that is linear variation. Now at x equals to 4, what should be the value? At x equals to 4, VC equals to minus 4 over 8. Okay, so it is nothing but minus 0.5. So at this location, the value is minus of 0.5. Okay, at this location, when x is just at the left of C, when unit load just at the left of C. Okay, then at that time the shear force when the unit load is just at the left, then the shear force generated is minus 0.5. Right? Now let us suppose our load comes Now let us suppose this loads comes at a distance of x from this location, this unit load. Okay, so when the unit load is at this position, I can write what will be same equilibrium equation: Ra plus Rb is equals to 1 unit load. This will be holding everywhere. Wherever the unit load is acting, this equation is valid everywhere. Okay, then if I take moment about this point, then it will be 1 into x equals to Rb into 8. Okay. From here again, Rb comes out to be x by 8. And again, Ra is nothing but 1 minus of x by 8. Okay. From this equation. Now, this is the equation Ra equal to 1 minus x by 8. Okay. Now, if I cut my beam, if I cut the beam at this section, this is our unit load, this is our B support over here, this is B point, and this is C point, right? So Ra will be nothing but 1 minus of x by 8. To balance this Ra, there will be some shear force at this point, this is BC, okay? And at this location, some opposite shear force will act at this point also, this again VC. Okay, so this is nothing, so this is what, so this is this at this point you can see that this is VC is negative. Okay, VC is positive. Okay, if I move from this point, you can say that if I move from this point, you can say that it is VC is positive. Okay, so if I take a small element over here, at this location, let us suppose. So this VC is acting in direction. To balance this force, some shear force will act in this direction. So this is positive shear force. Okay, Similarly, if I take one element at this point, so it will look like this. V is in this direction to balance this force. It is in the shear force will act in this direction. So this is also the positive variation. So at this location, when the shear, when load is acting, just right of this section, C section, it will be positive only. Okay. So from here, you can say that what will be the x at this location when the load is just at the right of C, just at the right of the C, then then you can say that 1 minus x over 8 is equals to our Ra, which is nothing but our shear force Vc. Okay. So when x equals to 4, so 1 minus 4 divided by 8, which is nothing but 0.5 equals to Vc. So at this point also, our the shear force is nothing but it is 0.5, right? So and you can say that the graph is again look like minus y minus mx plus c. So again it will come down in this direction. Okay. So when x equals to what you can say that when x equals to 8, this shear force is at this section will be 0. When the unit load will act at this support, okay, then the shear force at this section will be 0. Why 0? Because this load is taken care by this load completely. Okay, no load will transfer to the A, right? So this is our case. Now, when the unit load crosses this support B, and it will act at this location, then again at x equals to our 12, this is equal to 1 minus 12 over 8. This is nothing but 1 minus 1.5. So it is equals to minus of 1.5. Okay. So this graph will move like this, and this coordinate is nothing but this is minus 1.5. When the load is acting at this point, at this end, then the shear force generated at this cross section will be negative, and the value is minus 0.5. Okay, so you need to basically consider which shear force we are considering positive, which shear force we are considering negative. Okay, this thing you can see over here, right? So this is basically our shear force diagram. So this is 0.5, and this is here also it is 0.5, right? So when the unit load is acting at when the unit load is acting at C, then you can say that the shear force diagram took a sudden jump. Okay, that's why the shear force is not defined at this location when the unit load is acting at this point. Okay, why? Because I cannot tell what shear force is there. Okay, either we need to have left at the section C or just right of the section C, right? So this completes our the shear for the shear. This completes our the ILD for the shear force. Now we'll see what will be the ILD for the bending moment at point C, right? Now, this is ILD for shear force. Okay. Now we need to calculate what will be the ILD for the bending moment. Okay. Again, I'll draw that same beam over here, and this is the overhang D, and this is point C. This is 4. This is 4. Okay. Now, first again, I'm considering when the load is acting at this location at a distance of x from A support. Okay. So this is our unit load. So in ILD, basically we are moving the load across different sections. Okay, and just seeing how shear force is varying. Okay. From that only we can draw this ILD influence line diagram. Okay. So when the unit load is acting at this location, what will be RB? RB is nothing but RB will be x by 8 in upward direction, and RA will be nothing but 1 minus of x by 8, right? So now what I will do over here, I'll again cut the beam at this section, at C section. Okay, so the beam will look like this. Here one force x by 8, that is RB. This is D point, this is C point. And again this is A point, this is unit load at a distance of x, right? So if I take a moment about C, if I want to find a moment about C, this beam will need to be in equilibrium, okay? In the force equilibrium, moment equilibrium, okay? So for the moment equilibrium, if I find this moment about this point C, I can write it like this: RB into 4, and here some moment, let us suppose some MC moment will be there, and here also to balance that MC moment will be there. Okay, some shear force will also be there, but we are not considering that. Okay, so RB into 4 minus of MC will be 0. So RB is nothing but x by 8 into 4 minus of MC equals to 0. So I can write MC equals to x by 8. Okay, and the direction of MC is coming positive. Okay, these moments are producing sagging. Okay, so these are considered positive bending moments. Okay, these are considered negative bending moments, right? So this is our sagging case. So this moment is MC is positive, right? So MC is equals to minus of x by 8. So MC will be minus of x by 8. So when the unit load at a distance of an x, okay. So how we will draw this figure? At x equals to 0, when the unit load is acting at this support, okay, whole load will be taken care by RE. Okay, so the moment at the C will be 0, because moment due to this extra unit load will be balanced by this reaction force. Okay, the moment due to this reaction force. Okay, so I can write the moment will be 0 at this point when the unit load at this location. Okay, when the unit load is at just left of C, then the moment at that point will be MC equals to 4 divided by x equals to, this is 2, this is 8, and this will be 2, x by 2. So it will be x by 2, which is nothing but 4 by 2. So it will be 2. Okay. So at this location, the moment is 2 kilonewton meter, right? Now again we will see when we change the position of the load just right of this section. Okay. Okay. Again, this is our section C at a distance of an x. Let us suppose this is unit load. Okay. So again the reaction will be same. This is x by 8, and this here it is 1 minus of x by 8. Okay. Now, if I again cut this beam at this section, this is A, this is C point, this is B, and this is D. So here again the force is x by 8, some unit load 1, right? And let us suppose to balance this, one moment will act at this point, again one moment MC will act at this point. We need to find that MC moment. Okay, some shear force will be there, right? And this load is nothing but 1 minus of x by 8. Okay. Now to find MC, I have two choices. Either I choose this side or this section. Okay. My calculation will be easy if I choose this portion. Okay. If I choose this portion, then moment at MC will be nothing but if summation m equals to 0 about C, if summation m equals to 0 about this C, I can write 1 minus x by 8 into 4 minus of MC equals to 0. Okay, this is 1 minus x8 into 4. So it will be nothing but the value is 4 minus of x by 2 equals to MC. Okay. So when x equals to 4, the value is nothing but 2. Okay. Now you can see that again this curve is something like y equals to minus of mx plus c. So it will come down, right? So when x equals to 8, what will be the value? 4 minus 8 divided by 2, the value comes out to be 0. Okay, so when the unit load is acting at the point B, the whole load will be taken care by the support RB. The whole load will be taken care by this RB reaction. Okay, and those reactions will balance the moment at C. Okay, so this will be again 0 at this point. Now when x equals to 12, the moment will be 4 minus of 12 divided by 2. So it will be nothing but 6 minus 2. Okay, so at this point the moment is negative minus 2. Here it is positive. Okay, so this is our the influence line diagram for the moment. Okay, for moment, right? So this is the way you can draw the influence line diagram by using the direct method. You just need to write the function for the chosen reaction which you have chosen. Like here the chosen reactions are shear force and moment. Okay, so you need to write the expression in which we need to include the unit load and the positioning of the load. Through that you can find the shear force and bending moment at that particular section, and with the help of that you can draw the influence line diagram, right? So this is the basic problem in which we draw the influence line diagram using the direct method. Okay. Later we'll learn about Euler-Breslau principle also. Okay. Thank you guys.